In this example, we want to find the first and second derivatives of the function f of x equals x squared plus x e to the x divided by x to the fourth plus 1. The important thing to keep in mind here is this will be a quotient rule because it's a quotient, and then inside we'll have a product rule on this term x e to the x. Let's write out the first derivative with the quotient rule. So the first derivative should be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now we can put these two derivatives on top and simplify out our expression. So this will give us an x to the fourth plus 1. And the derivative here is going to be a 2x for the x squared. And then from the x e to the x, I will get the product rule. So I will get a e to the x when I differentiate the x. And then a plus an x e to the x when I differentiate the e to the x because the derivative of the x is still e to the x. Minus x squared plus x e to the x. That stays the way it was. And then the derivative of x to the fourth plus 1 is just 4x cubed. And the bottom remains the same. Now, since we want a second derivative, we want to simplify this a little bit before we actually get to that point to make sure it's easier to find the second derivative once we need to. To do that, we're going to group terms together based on the numerator, whether or not they have an e to the x in them or not, and then we'll expand the denominator into a trinomial term with 3 terms in it, make this easier to do. On the top, what I will see is this becomes an x to the fourth plus 1 times a 2x, plus an x to the fourth plus 1 times an x plus 1 times an e to the x, because this e to the x plus x e to the x becomes x plus 1 times e to the x. And then I will have a minus the x squared times the 4x cubed, which is a minus 4x to the fifth. And then I will see a minus 4x to the fourth e to the x. And the bottom here expands to be x to the 8th plus 2x to the fourth plus 1. If I expand out each of these terms here, I will get a 2x to the fifth plus a 2x plus a x to the fifth plus x to the fourth plus 1 times an e to the x, and then minus the 4x to the fifth and the 4x to the fourth e to the x. And now I can merge these together, combine terms of the same degree, to get me an expression like this. 2x minus 2x to the fifth. That came from combining this 2x to the fifth with this minus 4x to the fifth. And then plus x to the fifth minus 3x to the fourth plus x plus 1 times e to the x all over x to the 8th plus 2x to the fourth plus 1. So there is our simplified expression for the first derivative. Now the second derivative is going to also require the quotient rule. And to finish that, I'm going to need the derivative of the top and the derivative of the bottom, which I can then piece together with what I already see here to give me the actual formula for the second derivative here. So what's the derivative of the top? Well, the derivative of the top is going to be a 2 minus 10x to the fourth from that polynomial part at the beginning. And I'm going to get a product rule for this last bit. So I'm going to need to write the polynomial here as it is, times e to the x. And that's my differentiate e to the x. And then I want to add the derivative of that polynomial, 5x to the fourth minus 12x squared plus 1 times e to the x when I differentiate the polynomial itself. And then what's the derivative of the bottom? Well, that's just going to be 8x to the 7th plus 8x cubed. That's a standard polynomial. Now, what does this give me for my second derivative here? Well, there's our quotient rule formula, and now we can just stick in the different formulas we have for the different parts of the original fraction. So, f double prime should be, we get the bottom times the derivative of the top, minus the top times the derivative of the bottom, 8x to the 7th plus 8x cubed, and then all divided by the bottom squared. And that there is terribly messy, but that's the formula for the second derivative of this function. You can simplify things out more if you wanted to, but that would be sufficient for an answer to this sort of a problem.